All right, welcome to this month's PCAST talk. Thank you everyone for joining us. So today we're going to hear a little bit about time domain astronomy in the far infrared. And first we're going to give a few updates. So we're excited to say, and we're really grateful to the community for the success so far of the PRIMA General Observer Book, Volume 2. So we've received more than 120 submissions from the community of science cases that they can do across a wide range of science with PRIMA. So again, thank you so much for everyone who is involved in leading or participating in submitting a case. And if you did submit a case, you should be hearing from one of the editors of the GEO book, who will just be in touch to confirm that we received your submission and reach out if we have any questions. So we also have been having a busy summer at conferences, which is exciting. So we kicked it off at the end of May with PRIMA and the Future of Far Infrared Science. So again, we had more than 100 folks joining us in Pasadena, talking about all sorts of things that could be done with PRIMA. We also have been having special sessions, including one just this past week at the EAS, the European Astronomical Society meeting, where we've had, again, really great community participation and interest. So please watch as well for opportunities to promote or learn more about PRIMA at other upcoming conferences. So today we're going to have Kishalay Day, and so Kishalay is really a wonderful sort of rising star and expert in this transient science, and so he's going to be talking about all of the different ways that we can learn more with PRIMA and with the far infrared about this really exciting field of astronomy.
Yes, perfect. All right. Okay, thank you. Thank you to the organizers for inviting me to do this. I think it's an honor to do this because I think especially for the work that we've been doing, I think the infrared bands have turned out to be rather spectacular when it comes to time domain astronomy, and it's been really driven by a lot of technological advancements and also a slew of missions that are flying today and will fly very soon that are enabling a lot of these discoveries. So there's a lot of excitement when it comes to exploring the transient sky in the infrared. So I'll get started by giving you sort of a background as to why some of these discoveries are happening today and why this is really the right time for us to be thinking about PRIMA and what we can do in the far infrared by capitalizing on the synergies between surveys and what PRIMA can do. So the way I like to start this talk is to really just by showing the massive number of time domain surveys that are running today. So what you see here are a collage of different time domain surveys that have really changed the landscape when it comes to time domain astronomy. You've probably seen, heard of most of these things, and apologize if you're missing one of your favorite surveys. But the general idea is that it's when you look at the time domain sky in the optical bands, at least, there are enough number of surveys today such that for any part of the sky, you can basically be able to observe that part of the sky at least once a night. And a lot of this has been driven by these wide field optical cameras that are scanning the skies routinely. The picture hasn't been so mature in the infrared bands, at least historically. As you can see, most of the surveys that you see here, ZTF, Atlas, Assassin, PanSTARRS, they're all optical surveys. But the infrared scene has really changed only in the last few years with these the surveys on the bottom right, which are Gattini IR, which was one of the first wide field synoptic infrared surveys to scan the sky, as well as space-based efforts like NEOWISE, which wasn't really designed as a time domain survey because it was tailored to find solar system objects. But the scene has really changed because NEOWISE is now being used routinely to find transients, even as it did this survey to find asteroids in the solar system. So fortunately, the scene has changed in the infrared, and we are currently on this verge of essentially a revolution when it comes to infrared capabilities in time domain science. What I'm showing here is a plot that was created by the RAPID project infrastructure team for the Roman Space Telescope, which shows a timeline of the different surveys in the infrared bands that have operated in the past or are going to operate in the near future. What you see for each of these instruments, it shows you what bands it operated at, whether it was near or mid infrared, the depth that it was going to, which is in magnitudes that you see over here, what the field of view was in square degrees, and the total survey area that each of these surveys were covering. The main point being that if you look at the historical aspect of it, most infrared surveys in the past tended to be these single snapshot infrared surveys. We just looked at the sky once, but the scene is very rapidly changing because all of these new instruments that are coming online now, both from the ground and in space, are for the first time starting to do these cadenced infrared surveys that haven't been possible in the past, primarily because it's difficult to do infrared surveys from the ground because the atmosphere is bright, and also because large detectors are somewhat difficult to manufacture in the infrared. But what I really want to highlight is that not only are these capabilities allowing us to probe into a regime that hasn't been done before, which is the infrared time domain sky, but it also the kinds of discoveries that we are poised to make are really going to address some of the biggest unknowns in our understanding of the universe, and especially the questions that have been highlighted by the decadal survey. And what I'm going to specifically focus on in this talk is give you an overview of how we can capitalize on the discoveries from these infrared missions to address some of the key unknowns that were highlighted by the decadal survey, and especially how PRIMA, with its capabilities, would be able to address some of these questions by, again, following up on some of these discoveries that are being made by surveys that are operating today and will operate in the future. So the way I thought it would be nice to showcase this is to really highlight how PRIMA would be in a position to address multiple themes that were highlighted as the highest priorities in the decadal survey, all the way from our understanding of cosmic ecosystems, new messengers and new physics, and our own place in the universe, and how stars form and how planets form around stars. So for this talk, I won't be able to really show you all of the rich physics that we are poised to learn in these talks, but I wanted to focus on two of the most interesting science cases I could think of, because it really addresses sort of two of the extremes when it comes to our understanding of the universe, one side being supermassive black holes and the other side being stars themselves. So I'll start with this fundamental theme that I think we all think of in many ways, is how do galaxies form? How do supermassive black holes form in the centers of galaxies? And especially talk a bit about how transient bursts of light can be used to understand how supermassive black holes form and grow in the universe, and how time domain surveys are changing our picture of this phenomenon. So if you ask this question of how do supermassive black holes grow in the universe, there is no doubt that the majority of the growth of supermassive black holes in the universe is fueled by gas accretion. So the idea is that we have these supermassive black holes in the centers of galaxies. They sometimes they are in very gas-rich environments, so much so that within the sphere of influence of the supermassive black hole, all of this gas falls into the black hole. It powers luminous electromagnetic emission that we often see as what we call active galactic nuclei. And if you observe the population of active galactic nuclei, you can estimate that this represents likely the most dominant method of growth for supermassive black holes across cosmic time. Although I think, especially with discoveries from JWST today, it's becoming somewhat unclear how do supermassive black holes grow so quickly, and how does gas accrete so early in the universe. But one thing that has been discussed for a long time, but we're only now beginning to understand or probe, is this idea that if you think of the centers of galaxies, then not only is there a lot of gas in the centers of galaxies, there are also stars in the centers of galaxies. And you don't need to look any further than the center of our own galaxy in the Milky Way. What you see here is a real time-lapse image of what stars in the center of our galaxy do. The idea is that not only do these supermassive black holes live in very gas-rich environments, they also live in very star-rich environments, so much so that you have lots of stars that probe very close to the supermassive black hole itself. Now, the reason why this is important when it comes to understanding supermassive black hole growth is that every now and then you would expect that one of these stars, let's say roughly a solar mass star, would become unfortunate enough such that it falls close enough to the supermassive black hole such that it gets tidally disrupted and captured. And this is what we was first theoretically predicted many decades ago, but we can now almost routinely find in time domain surveys. The idea that you can get a star that probes too close to a supermassive black hole that gets tidally disrupted and then falls back into the black hole, producing luminous electromagnetic emission that we can find in transient surveys. These are now understood to be panchromatic transients. They emit all the way from X-rays to optical to radio bands and sometimes even gamma rays, depending on the type of object. And what I'm showing here on the bottom right is a collage of light curves of what we call tidal disruption events that have been identified in optical surveys. We have these luminous flares which reach 10 to the 43 to 10 to the 45 Earths per second. We primarily see the optical emission from these events because that's where our surveys are operating. But it is also understood that because these are accretion disks forming around supermassive black holes, most of the emission is actually emerging in the far ultraviolet bands, which is unfortunately not something we can observe directly because of intergalactic absorption. So if you wanted to ask how much does a black hole accrete during one of these events, then a question you can ask is can I measure the total energy output that comes from this black hole accreting this star onto itself? And can I use that as a tracer of how much mass was accreted, using your usual energy radiated to mass accretion conversion? But to do that, to answer this question of how much does how much of the stellar material accretes onto the black hole, I need to be able to observe these sources in the wavelength range where they emit most of their light, which happens to be the far ultraviolet, because that's what the accretion disk temperatures are. But this is unfortunately not quite observable because of hydrogen absorption. So this has led to what is historically been discussed quite widely in the literature, which is what is called the missing energy problem, which is this idea that if you take all of the optical and UV light that we can measure from these events and ask how much energy is radiated in total, you can overlay that. So this plot here shows the total energy emitted for these objects as a function of the mass of the black hole. And what you see is that compared to theoretical models, which are these solid lines that show you, that tell you how much energy should be radiated if you just take a one solar mass star to be disrupted and accreted onto a black hole, the amount of energy that we actually see, which is shown by the black points, this happens to be usually an order of magnitude or even more smaller than the amount of energy that we can actually measure from these objects, which is again limited to the optical and somewhat near ultraviolet bands. And so this is what is called the missing energy problem, the idea that we likely don't see most of the energy that these things are producing, which makes it quite difficult for us to estimate the total mass that is accreted in these events. And there are alternative solutions to these things. The idea that if you look at the very long-term evolution of these events, what you often see is that if you plot the far ultraviolet luminosity of these events as a function of time, there are often these very long-lived late-time plateaus where the idea is that a lot of the stellar material might not even be accreting during the peak of the flare, but might actually be accreting at very late times. We don't know. This is one of the solutions to this problem. The idea that the reason we have a missing energy problem is that we discover these sources around peak, but most of the energy likely is emitted at very late times through these UV plateaus. And but again, this is something that we can't really measure directly because we don't have the capabilities to observe in the far ultraviolet bands. So the ultimate solution to all of this is that we have to accept defeat at some point. The universe is ultimately opaque in the far ultraviolet and it's unobservable. But turns out that even if this radiation is not directly observable, the universe gives us some clues to understand this problem because even because of the same reason that hydrogen is so opaque to ultraviolet light, it happens that dust is also completely opaque to ultraviolet light. And what you can imagine is that because these events live in some of the dustiest regions of the universe. Even if you had tiny amounts of dust surrounding these events, the dust would be completely opaque to this far ultraviolet radiation, and it would re-radiate all of this light that we can't really see because of ultraviolet absorption. It would just re-radiate it at a longer wavelength that we hopefully. Oops, sorry. Sorry, can you still see my screen? Just
Yes, we can.
Oh, sorry, yes, sorry, yes. I just wanted to confirm. Yes. So, right. So even if you can't see the far ultraviolet emission directly from these events, we can use the dust as a probe of the far ultraviolet emission that does not directly reach us. And the way this works is that if you have TDs that are surrounded by small amounts of dust, then you can get what are called dust echoes. So some of the earliest efforts in this direction were actually done by ground-based searches, which is that you look at nearby galaxies with the highest possible resolution adaptive optics imaging, and you can look for flares in the centers of galaxies that appear only in the infrared bands without any appreciable signatures at shorter wavelengths. And it turns out that when you do that, you get flares that look like this. These are some of the early discoveries from NEOWISE, which show these luminous flares of infrared radiation that happen to occur in the centers of galaxies, in centers of nearby galaxies. And the claim is that many of these do not have any associated emission because they're completely, the central TDE is completely obscured by dust. But what we see is the reprocessed radiation at longer wavelengths, which emerges in the mid-infrared bands. So this is something that was done almost starting a decade ago, where there were beginning indications that there are populations of TDs which even though we can't observe them directly in the ultraviolet, we can infer their presence and measure their properties with dust echoes. And this is something that we've tried to industrialize in recent years by essentially using NEOWISE directly as a discovery machine. What we do essentially is that if you, what I'm showing on the right are images from NEOWISE. You take an image taken, let's say, last year, you subtract an image that was taken 10 years before, and when you subtract these two images, you see there are often these point sources that stick out that wouldn't otherwise be directly very obvious. And we can find essentially transients in the centers of galaxies using techniques like this. And this is something that has really allowed us to find large populations of dust echoes of tidal disruption events and ask, can we use them essentially as bolometers for measuring the energy output of TDAs? So this has led to some really remarkable and surprising results, which all bode well for PRIMA, which is to say that one of which is that these dust echoes of TDs are quite common, even though some of them are largely overlooked because we haven't looked at them quite extensively in the infrared. Here I'm showing an example of a light curve of a luminous infrared flare that occurred in a galaxy only 40 megaparsecs away, which is literally backyard when it comes to extragalactic transient astronomy. What you see here is this luminous infrared flare that occurred sometime in 2014, was completely overlooked for nearly a decade before we started looking for it in NEOWISE. But when you do the energetics and you do and you measure the properties of the event, it all is consistent with a luminous dust echo of a tidal disruption event that was completely overlooked for nearly a decade. It was just hiding in the infrared archives, and we can now. So this was work led by Megan Masterson and Christos Panagiotou, who are at MIT, and they showed that that these luminous dust echoes of TDs are quite common in the local universe, and with rates that are comparable to what we see in optically discovered TDs. So this is great because it not only shows you that there is this population of infrared TDs that have been historically overlooked, but because these are so luminous and probably these are the most luminous infrared transients in the local universe, these are ideal test beds to test our models of how dust echoes work in TDEs and make detailed measurements with infrared spectra. And this is really what has enabled the first mid-infrared spectra of TDEs to be obtained with JWST. So what you see here are a collage of mid-infrared MIRI MRS spectra obtained with JWST of these events. This is a collage of 4 events that of the many events that we identified. This shows the rich detail that we see in these events, all the way from these broad silicate emission lines at 10 microns to a rich forest of these narrow emission lines that come from high ionization lines in the gas. These are coronal emission lines that appear in the mid-infrared. But so there are 2 things that come out of this. One is that these coronal emission lines really confirm and tell us that these must be powered by supermassive black hole accretion, because these are really high ionization lines that require a hot ultraviolet source to be powering them. The other thing is that because we can observe these sources in the mid-infrared, where most of the energy output is appearing now because the central source is completely obscured, you can use essentially the infrared radiation as a bolometer for the central radiation that we don't actually see. And this is something that we are starting to do now with these more sophisticated models of dust echoes of TDEs. The idea is that whenever you see a dust echo from a TDE, what you're seeing is essentially these iso delay surfaces, which is that the light that we are seeing actually comes from a range of distances from the supermassive black hole itself, because what you have is the light from the central radiation that is being absorbed and re-radiated by the dust as thermal emission, and it reaches us from a range of distances from the black hole, because of these are essentially constant delay surfaces of the radiation that is reaching us. And so what this allows you to do is to create consistent models of what we see in these infrared spectra are essentially a combination of dust emitting at very different distances. So what you see here on the right is the actual JWST data for an object overlaid with a superposition of 2 models. One is this sort of cool echo, which is coming from dust that is emitting at some distance away from the black hole, which you see on the left plot. And so that explains the longer wavelength far infrared or mid or far infrared emission. And that is superposed with some a shorter wavelength emission that is explained by dust that is emitting closer to the black hole, likely powered by these long-lived plateaus that we see in the ultraviolet. So this is essentially a hot echo of powered by ongoing accretion. And the main point being that we need a combination of this shorter wavelength emission as well as the longer wavelength emission to really understand what the total energy output of the event is. So what I'm showing here is a model for how this echo evolves with time. So you sort of take that previous model that we were looking at and you let it evolve over time and ask, how does the dust echo change over time? And what you see is that even though this dust echo is initially very hot in the sense that it's very luminous in the neowise bands and the mid-infrared bands, in a few years, it becomes, because this dust is now emitting at larger and larger distances from the black hole, in a few years, it essentially becomes cool enough so that it gets dominated by emission that is not even in the JWST band anymore, which is over here, but it moves completely to the PRIMA band, which is what you see over here, which is that in a few years, about a decade or so after, because the echo of this dust is moving further and further out, most of this radiation is now coming out in the far infrared band, and that's the region where PRIMA will only have the capabilities to observe this echo. So I overlaid this rough sensitivity plot for what FIRES would see, and we'll get back to this plot in a bit. But this just shows that how PRIMA, because we now have this sample of infrared dust echoes that we can routinely identify, PRIMA will have the capabilities to observe this late time dust echo. So a common question that I often get is, can we even tell that this is that if you saw far infrared emission from a galaxy, that this is actually coming from some sort of late time dust echo of a TDE? And so we ran some of these models more recently, where what I'm showing here is a model which was created by Megan Masterson. What you see here is on the top a luminosity plot, which shows the luminosity evolution as a function of time for these TDEs. It includes both this early time decay followed by a plateau that sticks around for about a few decades. And what you see in the bottom panel is a prediction for how the far infrared echo or the infrared dust echo would evolve. It starts off as this luminous dust echo that's visible mostly in the near and mid infrared bands. But as the time progresses, what you see here is that in these colored lines is the time progression of this echo, which very soon becomes dominated by far infrared emission. And just to compare, these black lines show what the predicted SED of a typical star-forming galaxy would be. What you see here is that these dust echoes are typically much more luminous than what you expect the stellar or star formation contribution to the far infrared emission to be. And there are two things. One is, of course, that we know that some of these have had infrared echoes in the infrared light curves showing TDs in the past, so you can actually you can use that as an indicator that there should be a far infrared excess coming from some sort of tidal disruption event echo. And that these are obviously evolving with time, which is something that is not you would expect from just quiescent star formation in galaxies. The main point being that these events completely outshine the galaxies for many years. And what we would want to do essentially is to do a combined PRIMA plus JWST campaign that would allow you to simultaneously measure the far infrared contribution to the dust echo in conjunction with the mid-infrared contribution which JWST can observe. And PRIMA is the only instrument that we will be able to get to constrain this far infrared component. So one of the programs that we put in for the GeoBook was to have a program where we take this sample of neowise dust echoes that we've identified almost 20 years ahead of PRIMA. That's great because we expect about the echo to move from the mid-infrared to the far infrared bands in about that time scale, about 10, 20 years. And we have a sample of about maybe 100 of these events that we've confirmed are likely TD dust echoes. And the idea would be to get FIRAS low resolution spectroscopy of the order of a few hundred events, maybe even 1,000 events, depending on the actual sensitivity. And these wouldn't have to be particularly time-sensitive observations because these are events that have occurred a long time ago, but they're essentially utilizing the synergy between PRIMA starting in the next decade and this lineup of many infrared surveys that have come before PRIMA. And the overall goal would be to measure the total energy output in TEs with this combination of mid-infrared and far infrared measurement of the bolometric dust emission at very late phases when PRIMA would be the only instrument that would be able to make these measurements. All right. So that sort of sets the first part of my talk, which is what do we learn about supermassive black holes and the growth of supermassive black holes through far infrared measurements, especially when it comes to eruptive transient phenomena. The next part of my talk will go to the other side of the scale, which is really to the smallest things, which are essentially stars and how stars form and live in the universe. And this is something that's, again, quite integral to the priorities that have been highlighted in the decadal survey, which is understanding our own place in the universe, how stars form, and their relationship to these new messengers and new physics that we are learning today. And what I'll focus on is this population of eruptions that we now understand to be caused by mergers of stars and how they might be very common in the universe. So for those of you who have not thought of stellar mergers on a regular basis, I just want to stress that stellar mergers are not just another phenomenon that transient astronomers have sort of just found and find interesting to follow up. There is a lot of evidence from independent directions of astrophysics that indicate that mergers of stars should be common in the universe. And so some of that comes quite fundamentally from looking at stellar populations themselves. So this is a plot showing from a recent paper that shows the color magnitude diagram of open star clusters in the Magellanic Clouds. What you see here is that even though you would expect star clusters to be fairly homogeneous stellar populations, what you see is that even things like the main sequence on this color magnitude diagram are quite broad, in that instead of having a single main sequence that you would expect from a uniform stellar population, what you see is that the main sequence of stars in any young star cluster tends to have this breadth to it. It's very wide. And it's not always clear why a uniform stellar population should have a main sequence that looks so substantially different? Why do the stars of one kind look different from the other? And the emerging consensus is that the way to explain why star clusters look like this is this idea that you have this population of normal stars, which are formed out of the traditional way of star formation, which is how gas clouds collapse and uh, coalesce into stars. But you also have this population of bluer stars that emerge from essentially what are mergers of first generation stars, and they tend to represent about something like somewhere between 20 to 30% of the stars in any star cluster. So these are not sort of a small delta effect. If about a third of stars in any star cluster form out of mergers, then it's quite a substantial effect when it comes to understanding stellar populations. So this is, of course, from the point of view of understanding just stellar populations in the nearby universe. The other reason we know that stellar mergers or essentially coalescences of stars must exist is because of the multi-messenger universe, which is that we know that we've observed now mergers of neutron stars, mergers of neutron star black holes, mergers of black hole objects, and the one of the most feasible ways to form these objects in the first place is this idea that the binary systems that form that lead up to these objects must undergo this phase where one star essentially is engulfed by the other star in what we call common envelope events, which essentially allows them to spiral in and come to these close separations that are needed for these objects to be able to merge within the Hubble time and for us to be see the multi-messenger universe the way we see it is. So there is quite wide evidence that coalescences or mergers of stars must exist. And of course, if you just wanted a bare bones proof that something like this must be quite common, you don't need to look any further than the remnants of most stars. So these are remnants of low mass stars that we call planetary nebulae. What you see is that when you look at high resolution observations of planetary nebulae, they quite ubiquitously have these remarkable shapes with these bipolar outflows and all kinds of rings and structures, which is somewhat difficult to understand if all of these were coming from, say, a single star evolution, which should just a single star should just eject its outer layers and die as a spherical nebula, but that's really largely not the case when you look at remnants of low mass stars. And the idea is that a lot of this shaping of the outflow that these post-AGB stars do at the end of their lives is shaped by the presence of a binary companion that is essentially engulfed by the primary star as it is dying and ending its life. So if you wanted what a simulation of this might look like, just to give you a sort of a cartoon picture of it, this is a simulation of two stars merging into one object. What this shows is that you have a star that becomes puffed up and giant enough so that it engulfs its companion in some sort of an envelope. And this star eventually spirals into the envelope of this primary star and then ejects its outer layers, and you get this potentially luminous transient that can be powered by these outflows that we see. And what you see here now in the background is actually a real time-lapse image. This is not a simulation anymore of what we think was a stellar merger in our own galaxy. This is this eruptive star known as V8381. It was an eruption that happened about maybe 20, 25 years ago. What this shows is a time lapse of Hubble Space Telescope images of the eruption itself. The main things to take away from this is that this expanding nebula is caused by a light echo of this eruption reflecting off of nearby gas clouds. The other thing being that what you see is that this transient becomes very red very quickly. You see the emission, the HST images themselves tell you that the transient is very red if you just look at the central object, the super bright central object in the center of this nebula. So this is what we call luminous red novae, essentially because they look like novae in many ways. They have these eruptive outbursts, but they also become very red with time and hence giving them their name, the red novae. And these are quite routinely discovered now in optical surveys, something of the order of a dozen objects every year in optical time domain surveys. The way we identify them is again using this characteristic picture that they have very red emission. So if you look at the light curves of these objects, so this is a light curve of what we believe is a luminous red nova in the galaxy M31. If you look at the light curves of these objects, they have these remarkable optical outbursts, which last for about a month or two. But because this object becomes very red very quickly, they have these very long-lasting infrared afterglows that essentially last for years and sometimes decades, depending on the luminosity of the event. Again, the general idea being that in this process of two stars coalescing into one object, you get this remarkable outflows that throw out all of this gas, and this gas goes out and forms dust. So all of this long-lived infrared emission comes from dust that is forming in these outflows. And the discovery of luminous red novae is now quite routine in optical surveys, although there is now increasing evidence that what we see in optical surveys is only a fraction of the picture when it comes to the total population of stellar mergers that are out there. And evidence for this, again, comes from looking at the progenitors of stellar mergers that we see in the nearby universe. So this is a plot from a paper that I did with my colleague Morgan McLeod a few years ago. What this shows is our HR diagrams of, well, these are stellar evolutionary tracks of stars of different initial masses. What you see here is in the lines, these are theoretical models, and overlaid on that with diamonds are actual progenitors of luminous red novae that have been discovered in optical surveys. The main thing to take away from this plot is that most of the progenitors of luminous red novae that we see in optical searches tend to be somewhat more compact stars, things that are crossing the Hertzsprung gap or become on the subgiant phase. But for the longest time, there's been this lack of events that come from stellar mergers that are occurring on the giant phase when stars become really big in size. On the red giant and AGB phase, that's when the stars typically have their largest sizes, but we don't usually see stellar mergers from that particular evolutionary phase. And the point being that optical searches have likely missed some of these events because as the stars approach the end of their lives, they can because they have these large giant envelopes, these envelopes can form a lot of dust that leads to this entire outburst being obscured even before the optical transient can be seen. And these are the kinds of things that are precisely being enabled, the discovery of which is being enabled by infrared time domain surveys. So the idea is that these stellar mergers that come from giant stars must exist out there, but you really need infrared capabilities to be able to find these objects because these are likely obscured by dust even before the final phase of the merger produces the outburst itself. So this is something that's again being enabled now because of the emergence of infrared time domain surveys like NEOWISE, ground-based surveys, where we can now look for luminous outbursts of nearby stars that are likely caused by mergers that are happening all the way in our own galaxy to nearby galaxies. Here is a plot showing what we believe is a stellar merger, a powered luminous infrared transient that has been identified in NEOWISE. You see there is this luminous infrared brightening that we see in WISE data, particularly in the longer wavelength bands. And that's even true now from ground-based surveys. So ground-based surveys that are now monitoring nearby galaxies can also find these outbursts that are being powered by mergers of stars. So the entire reason why the infrared, again, is fundamental to understanding these objects is because, as we saw earlier, these transients are predominantly powered by infrared emission because of all of the dust and gas that is ejected in this process. And the way I like to think of this is that you have these two stars that have sort of merged into this much of gas that surrounds this binary, potentially surviving binary. We don't sometimes, in most cases, we can't really tell whether there's a binary that's inside or it's merged into a single object. But the only way to understand what the long-term evolution of the system looks like is by looking in the mid-infrared and the far-infrared bands, because that's where this cold gas and dust is emitting. And we know this specifically because we've, at least for maybe one or two galactic objects which have been nearby and were fortunately erupted at a time when Herschel was observing, which was a long time ago, we have measurements of what the the SEDs of these objects look like. Here is a measurement from a recent paper which shows what the remnant of a stellar merger looks like. What you see is that even though this sort of was identified as a luminous optical object initially, within a decade or so, it becomes completely dominated by far infrared emission. So this is the shorter wavelength bands is where they become completely optically invisible. And they almost become invisible even in the JWST band because when once dust cools, it becomes completely dominated by the longer wavelength emission. And the PRIMA band is really where these things shine for decades after the outburst. So you can imagine there are lots of these the stellar merger remnants that are floating around in the Milky Way, just dominated by far infrared emission that we don't actually see even in any other survey because they're dominated by far infrared light. So, so I overlaid here what for events that are identified using time domain surveys that are operating today. You can overlay what the sensitivity of PRIMA would be for spectroscopy of these events. As you can see, understanding the fate of this remnant, whether how this gas is ejected and what that means for the products of these stellar mergers is something that it can only be addressed with far infrared follow-up because that's where the dust and gas is emitting. We want to measure things like how much gas is ejected, how much dust is formed. And the question of dust formation specifically is likely even more interesting because if you look at the typical SED of a stellar merger, this is a plot from Ryan Lau and Viraj Karabelkar. This is also one of the chapters in the geoscience book. What this shows is the remnant of a stellar merger seen many years after the outburst. Again, you see that it's completely dominated by far infrared emission. And what you see here on the left is the sensitivity of phi-res in the low resolution mode, which shows you that phi-res can easily detect the remnants of these events, especially as the dust becomes cool and it becomes dominated by far infrared emission, especially in the context of understanding whether these could also be factories of cosmic dust. The idea that if you take a typical stellar population in a galaxy, we know that AGB stars form some amount of dust. Perhaps supernovae form some amount of dust. That amount is not well constrained. But what this right plot shows you is the amount of dust that might be formed as a function of the age of a stellar population, just because of these repeated mergers happening in young stellar populations. And that could potentially even be the contribution of this dust could even dominate or be as comparable to what we believe is the domination is the contribution of core collapse supernovae in forming dust early on in galaxies. All right, so again, the broader program here that we are trying to address is being able to capitalize on the synergies between PRIMA launching in the next decade and this slew of precursor surveys that is allowing us to find these luminous red novae years ahead of the outbursts so that we can follow them up with PRIMA when they become dominated by far infrared emission in about a decade. So the idea would be to take this sample of luminous red novae that we identify in surveys today, both from the optical and infrared bands, take a complete flux limited sample of these objects within about, let's say, 50 megaparsecs, and be able to do phi-res observations, low resolution spectroscopy of the order of 100 events at phases of the order of a few years to a decade after the eruption. Again, this is not something that is time sensitive because these are events that have occurred a long time ago. But again, the far infrared emission is critical to understanding the total gas and dust budget that is produced in these events. And the idea would be to use the far infrared continuum as a probe of the ejected gas to quantify the dust production, as well as to understand how do these merger remnants approach their final state as either a sort of a merged star or potentially a surviving binary that is left behind. All right, so yes, so this is sort of the summary of my talk. I think what I was trying to focus really on is that these far infrared follow-up of discoveries that are happening today and will happen in the near future so far infrared follow-up with PRIMA is really going to be the only way to understand some of these unanswered questions when it comes to our understanding of the growth of stars, the growth of supermassive black holes, and really address some of the highest priorities that have been highlighted in the decadal survey. So with that, I will end there, and thank you. you can't hear you. Yes.
Yes, all right. Thanks so much, Kishalay. And folks, you can go ahead and ask any questions or put them in the chat, and I'm happy to read them. So I wanted to ask, so PRIMA sort of nominally as a 5-year mission. So what sort of cadences, especially if you had sources that you found and you wanted to monitor them, what sort of cadences might you be looking at for let's say some of the stellar sources?
Right. Yeah. So that's a good question. I think for the science cases that I presented today, the cadence is not really something that is important at all in the sense that I think a lot of the science questions that we're talking about, they benefit from really long baseline observations. So even something in Prima year 1 and Prima year 5, like even like two individual epochs separated by separated at the start and the end of the mission is going to be sufficient for addressing some of these science questions, especially because I think by the time these objects become dominated by far infrared emission, they're already very old. So what we're really looking for is to understand the long-term evolution of these objects. So it is time domain, but in the sense that that it is evolving over very long time scales, especially for the science cases that I discussed today.
So what are your thoughts then on sort of an all-sky survey with PRIMA, especially since you're talking about cases that are both sort of like in and out of the galactic plane, right? In terms of both
Yes,
looking at,
yes,
at stars and black holes, which sort of
yes, yes.
suggests that not simply a wide area extragalactic or a wide area galactic survey might cover some of would cover all of those areas.
Right. Yes. So I think so I think that so far I think this talk was focusing on Prima as a follow-up capability. I think what the All Sky survey would be particularly good at is as a discovery capability, in the sense that there is good reason to believe that you know that things like stellar mergers are fairly common. Yes, the rate is probably once every few years in the Milky Way, and so you can imagine that within the last century, there are probably of the order of 20 or 50 of these stellar mergers that are just floating around in the Milky Way, and we don't actually know where they are because we haven't had century-long time domain coverage of the galactic plane. So I can totally imagine where if you had a full sky map with Prima of the galactic plane, you'd be able to pick out these remnants of stellar mergers that have occurred decades ago, because that's really one of the things we want to ask, which is that we clearly see evidence of these stellar mergers in stellar populations as sort of the remnants that are probably many thousands of years old. But there are definitely things that should have occurred in the last century or the last few centuries would be quite distinctive signatures in the far infrared bands if you had access to a survey like that.
Excellent, thank you. All right, we have just a couple more minutes if there are any last questions.
Hi, Shija from Roma. Um, because I don't find how to book.
Difficulty hearing you, you can type your question in the chat.
Okay. You can hear me.
Am I hearing? Can't hear. The question was.
Okay.
Okay. Right. Yes. Yes. So I think, yes. So for the science cases that we discussed here, we're really looking at very slow cadence follow-up in the sense that even if PRIMA was a 5-year mission, we are really thinking uh, of an approach where you, let's say, you do it twice or thrice over the entire 5-year mission, especially because we are targeting objects that are sufficiently old. But again, it's these phases where they become dominated by far infrared emission. So we're really interested in like maybe getting one observation even once a year. That would be more than enough for many of these science cases.
Because for, I don't know if you can hear me, because for some really faint a remnant, in a colleague of mine 2 years ago said that they need 45 to 100 exposure time. I don't know if kits may be performant enough, but so much time also have stability, and those things are geometrical, are small, simply small. Thermally interesting, but geometrically small. I don't know how to translate it in astronomer's language. Sorry.
Right. So I'm trying to. So yes. So yeah, are you talking about the exposure times necessary? Is that what your question was about? It wasn't. Right.
Yes.
Yes. I think because these are very slow evolving objects at the phases we are trying to look at. I think the kinds of exposure times we were thinking of is like a few hours per object. So a few hours per object separated by a few years is enough.
That's good.
Yeah.
Because
Yes.
for wonder, then my mind's wondering if we can expose in different seasons, trying to get different positioning for those binaries you shown in the latter part of your note. That's good.
Right. Yes. Definitely. Yes. These are not. These are very slow evolving objects. So in principle, you can split up that few hours of exposure time over a year or something. I don't think it would matter much.
That poses some criticalities between self-calibration of those sources in different season prevalence. I don't know how you pull the geometry variation in per year. Okay,
Right.
that's enough.
Yeah.
Thank you.
Awesome. Well, thank you so much, Kishalay, and thank you everyone for joining us. And the recording will be posted along with other PCAST recordings online and on our webpage. Thank you, everyone.
Thank you.